it goes through the blast furnace. So we charge coke and agglomerate in this reactor. We inject very hot gases at the bottom with combustions operating. And then with the descending motion of the agglomerate and coke, we have agglomerate going from a solid to a softened solid, then to a liquid. And the energy is brought by, in fact, the coke that are where combustion occurs at the bottom of the furnace. Once we have the pig iron, which is liquid raw material for the steel, we have several other steps in the processes where we add chemistry, and so it's called secondary metallurgy. We also have another material that we can reuse. As you may know, steel can be recycled, so we are using some recycling steel, which is named scrap, to add also in other melting processes. And sometimes we have a mix, so we use pig iron, then mix with some scrap, depending on the composition we want to make. Once we have the liquid steel, we are going from a liquid to a solid by solidification processes where we are cooling the steel in a very specific piece. So here you have the products we are making. It's like it's called slabs. Depending on the geometry, it's called slab, blooms, or billets, but it's a very thick piece of steel, in fact. Okay, so just for understanding what is the steel, and so here you see we have particles, in a lot of parts before the blast furnace, and a lot of things remains not known in some of these processes. On dit une brame. Ouais, ça c'est une brame. Et billette. Billette. Et bloom, alors c'est un cylindre plein. So now we are going to decarbonize this industry because it's quite energy intensive and also generate a lot of CO2 emissions. And then we are studying new processes in order to modify and use less carbonate material. To do that, we are changing the processes. So instead of doing sintering of iron ore, we are going to pelletization. Then instead of using blast furnace, we have tried to split the blast furnace in two different processes. One for reducing the material, which is called the direct reduced iron process. Then a second process is to melt the reduced iron. So we are going from an oxide to a reduced particles of iron, then we melt it. Then we have the same chain of processes after. Okay, so just to give you an overview of what we are interested in fact, in the steel and the chain of processes that we are working on. So as you may know, the steelmaking is responsible for 10% of global climate-related emissions. So CO2 mainly, but other dust and let's say problem of emissions. So we need to find new ways to recover the energy from these processes and also to study new processes in order to reduce as much as possible the CO2 emissions. So what I'm currently doing at ArcelorMittal Mézières is to study specific processes And we are doing some experiments and simulations in order to better understand these processes. So we are interested to validate our modeling approaches and doing some relevant experiments for these processes. And I will focus my talk on two of these processes that involve gas and particles. To give you more context, I'm showing some numerical strategy across spatial scales for particles fluid systems. So if we want to really solve all the Navier-Stokes equation around the particles, we have the possibility to make Euler-Lagrange simulation with full resolution of Navier-Stokes. But we can resolve mainly few particles, let's say 100 maximum, from what is in the literature. If we want to go to larger scale, we can degrade a little bit the fluid by doing some unresolved coupling between Euler and Lagrange simulation. So the particles are smaller than the grid cell size. And we can simulate around 1 million particles. And we can assess the scale of around a meter. And if we want to go to very high, large lengths, let's say, we have the possibility to think about doing some Euler simulations with good closure relations for particle fluid. So for the simulations I will present, we have, because the scale is about a meter, we have used this unresolved CFD-DEM model, which is a mean description of the fluid with turbulence model. And we solve the granular flow with particle scale method with Lagrangian description with drag force models. So I will present this this method in the context. Then I will go through the two studies I was mentioning before. So here we have, on the one hand, we are using the discrete element method. So we describe the particles with the Lagrangian motion. We solve the Newton's second law of motion of each of the particles for each particle I. So we have the different forces, the gravitational force, the contact force. We are using Hertzsprung contact force model and the particle fluid drag force, which is GDASPO1. So it's a combination of the Wen and Yu and Ergun drag laws. And on the other hand, we have the CFD, computational fluid dynamics, based on Euler description. So we solve local averaging Navier-Stokes equation that are shown here. And the coupling term, in fact, between the discrete element method and the CFD are the particle fluid flow, so the drag, which is present here in the motion of the fluid and here. So it's the terms that couple both approach. And here you can see that, in fact, the particles are smaller than the grid cell size for the fluid. And typically, we are using 2 to 3 particle diameter to define the grid cells. So practically, how it works, so we know the distribution of the particles. We can evaluate the fluid flow. We can evaluate the drag force calculation. And we can apply this drag force on a certain number of time steps, delta p, to make move the particles with the contact force calculation and the movement. Once we have done enough time step to meet the fluid time step, as the particle time step is smaller than the fluid one, we estimate the volume fraction of the solid in the cell then we can solve again the Navier-Stokes equation averaged, then we do another cycle. So it's the procedure for this kind of methodology. So I will be using this approach then for the two different topics I will talk about just after. So here first I will discuss an application on the simulating a pilot, a blast furnace pilot. So this work was done by Francis Romano, who did his PhD on the topic, and Pascal Fédé from IMFT also worked on the topic. So here, let me give you the context of this process. So these are the industrial observations. So we have the blast furnace that we charge coke and iron ore at the top. We inject the gas at the bottom where the combustion occurs of the coke. And in fact, at the very bottom, so it's a quite harsh environment because you have the combustion occurring, so you have 2000 degrees C. We inject the gas at 200 meters per second. And from the measurements that are available, so we can use a laser to measure the lengths of a cavity that are created when the gas is injected. This cavity is about 1 meter of size. And from core boring, we can extract some particle size. And we know that the size is about 35 millimeters close to the border. And we have a very fine particles area on the rear of the cavity. So that's the different observation at the plant scale. But it's difficult to measure the shape of this cavity at the scale of the plant. This is why I have some colleagues that worked in the past to develop. So the raceway is the voids that are created when you inject the gas at the bottom of the blast furnace. You have many raceway around the circumference of the blast furnace, and in front of each of these tuyères, you are building a sort of large bubble of porosity when you inject the gas. So that is called the raceway phenomena in this industry. And due to the difficulties to measure in the field, we are using some pilot scale experiment. So it's colleague from me that developed that pilot in the past. And so you see it's like a 2D slot model. You put some coke at the top of the you charge the coke at the top. And you can inject the gas on the side. And there is a quartz window where you can have a look to the cavity that is created. So the particle size that is used is a bit smaller than in the real application, but it provides some interesting results. So what is observed in this experiment, we have, in fact, when you inject the gas, there is combustion occurring. So there is a growing cavity. And at some point, at a given size of cavity, we have a collapse of this cavity suddenly. And the cycle restarts again. So you have combustions, enough combustions, and a collapse. So we have successive growing and collapsing of this raceway. And what is measured in this experiment is the pressure close to the nozzle. And this is the graph you can see here. So in fact, as the pressure decreases, as the cavity expands, then suddenly we have the collapse, and we have an increase in the signal of the pressure that is measured. So in fact, we can measure some amplitude and time between two of these collapses. So it provides some interesting data for simulation and to validate simulation approaches with in a case which is very, very close to the process. So when so we can build this quantity, which is the mass between two collapses. So this mass is in fact not linear with the flow rate. So what we observe is that at small flow rates, we have a kind of plume shape in front of the injection. And if you increase sufficiently the flow rate, you end up with a kind of big bubble. So that's what we observed in this pilot. So here I'm showing some simulations that we use CFD and DM coupling. So we have reused similar geometry. So you see that the pilot is about 2 meter height. And here you have the distribution of the particles we have used. We have been doing some. You have some details on the choices. So the density viscosity is taken constant. The model is incompressible, and we use the K-epsilon turbulence model. And you have here some information on the time. So we are using almost 1 day to simulate 2 seconds on 1 GPU of calculation, and we have 200,000 particles in this pilot. So here what we have done is first step-by-step analysis of the force acting on the raceway. So we did a simulation by only taking into account contact forces between the particles and the drag force with a geometry imposing a geometry of the raceway. So we imposed a wall first. Then you will see that this wall is not enough to extend this cavity. So we had to add other forces. So I will show that we'll have to add some cohesion force to have the balance. Then I will show what we have done for the coke consumption model. So here first, if we look to the distribution of the constraints in the fixed cavity, so we impose the raceway with the wall, we inject the gas, and we measure the different contributions. So on the left side, you have some profile of the constraints on the granular material. What you can observe is that we have the granular material is experiencing a Janssen effect where the pressure saturates because the pilot is very narrow, so that the distribution of the forces are toward the wall, so that the constraints that are experiencing the particles are not following, a sort of granulostatic pressure, but very limited pressure due to this effect. The other thing that we can notice is about the fluid. So we have 2 counter-rotative flow inside the raceway. So that's what we have observed. Then when we remove the imposed raceway at that moment, what you can observe is that we have a collapse of this raceway. So what we have prescribed is the geometry of the experimental raceway. So we thought it should stand, but in fact it doesn't. So that's what we have the results we have. And if we look at long time, in fact, we have 2 counter-rotative movement of the particles in front of the injector, And this is observations that are in accordance with other CFD-DEM simulations done by Hilton in 2012. So what we did, in fact, to try to reproduce the experiment is to add a cohesion force. So we here in blue curve, you see it's the contact force we have applied in the model. So the force as a function of the overlap. And we switch from Hertz-Midlin contact model to a cohesion model. So we have used Jensen, Kendall, and Roberts model. And so you see at on overlap 0, in fact, the force is negative. So it means that we have a cohesion force that tends to retain the particles between each other. So that's the model we have used. And we impose also some cohesion at the wall with similar values that in between the particles. So here you see some results. So with cohesion on the left, without injection of the fluid. So what we can observe is that we have a sort of collapse still, but when we inject the fluid, we have the cavity that able to stand. So it means that there is a balance between the drag force, the cohesion, and the contact forces in this system. And also, if you look at the collapse here, it looks quite vertical as in the experiment. So it is also something we think it's something relevant. Okay, so it means that we have a sort of phenomena that where we have a sort of cohesion layer at the raceway interface to have this balance working. Then now, to compare with the pilot scale, we need to add the consumption of the particles. So what we used is a simple combustion model. So we just reduce in size the particles with a very simple equation. So we just have a time which controls the reduction in size. And what we fix is a cylinder, in fact. So we have a cylinder that can inflate or decrease in size. So the central point is fixed. And in fact, the cylinder can increase or decrease the size. The only thing that is matching is a targeted mass flow consumption rate. So it means that if the consumption rate at time t is lower than the ones that are prescribed, that it will inflate, and the opposite if it's below. So in the simulation, when the particle is lower than 1 millimeter, we just remove them from the simulations, taking into account in the balance also to have a good mass conservation. Which is quite important, but because the lower particle size, the lower time steps you should take for the granular material. So we need a little bit to test that. So now, by the positive point with that is that we can play with the combustion, and we can also accelerate it a lot in the simulation with this model. And here we have so include all these parameters or contact, drag force, cohesive force, and coke consumption. And here what you can see is that we have a build up of cavity, and at some point we have some collapse. And it is something that repeats in cycles like in the experiment. So it is, let's say the observations are qualitatively good. And if we look at the pressure at the nozzle, we have some, once the cavity expands, we have a decrease of pressure and a sudden increase when we have a collapse, as we have found in the experiment. And also, if we only plot the very fine particles, we see that the very fine particles are projected towards the rear of the cavity. Here, only the fines are displayed in a calculation that we did. And here, it looks like a shape that is close to the fine particles that are shown in technique de l'ingénieur for blast furnace. So it looks quite good, let's say, qualitatively. But also, if we plot the mass between two collapses as a function of the flow rate, we see that we have a good agreement with the experiments. And also, if we look at the shapes, so at small shapes, we have a sort of a plume that we can have. We have the same in the simulation. And at larger flow rates, we have like a balloon. And here you can have the time. So some nice videos of that. So the destabilization mechanism depends on the flow rate, and the numerical raceway shapes are similar to the experiment. So that's quite interesting, because now we know that we need to include all these effects for this kind of simulations. And then what we try to do is to make some industrial scale simulation with this the similar phenomena. So here we have a very, the scale of the furnace is 32 meters. We are only considering a portion of the reactor, and we are simulating 1 million particles, and we have done some assumption, of course, on the particle. On the particle size a little bit, but mainly we have the good sizes close to the raceway with the good constraint in the pilot. So we are using contact force, drag force, cohesive model, and consumption which is accelerated in this model. So we inject the gas on one side, we fill at the top, and we prescribe the same combustion rate as we are filling at the top. You see we have two distribution of particle size, so this is an assumption, but we are interested close to this area. The objective was to obtain the good constraint on the particles and only that. And we have also used the spherical coordinates for the combustion model as we are in 3D now. So that's what we have done. And you have you can see the sphere radius as a function of time can move a little bit, but the mass consumed is constant with time. It's just to show you that this model is working. Then what we have done is here, so you have so with the cohesion, so we have added the same cohesion as in the PhD of Francis, and you have a video of the flow. So here we are looking all the particles and the velocity, and on the right side we are only looking at the particles that are getting burnt in the model. So we have not shown all the other particles. So different things can be seen is that first we don't have a cycle of collapses, but rather a continuous flow. And the practitioner of the blast furnace think that the flow is continuous. They don't have so much information, but we don't have a very big, bubble collapsing inside the furnace. So that's what they think, and what is in the literature also. So we have observed the same thing, that we have a quite continuous flow. And we have also the finds that are going, at the rear of the cavity. So that's what we have observed. And an interesting thing also we have performed is without the cohesion. So we can do the same simulation without the cohesion. And what is quite interesting is that you see that the fine particles that are generated due to the combustion, in fact, they percolate through the bottom. And so it means that they cannot build at the rear of the cavity. So we have observed that, in fact, the cohesion is important to obtain this small particle phase at the rear of the cavity. that to some extent controls the gas flow because it redirects the flow from horizontal to vertical. So the cohesion seems important, but only for the small particles behavior. But of course, there is a lot of works to continue in this field. So what we have shown at the pilot scale, the drag force is not enough to create to make stands the raceway. We need a cohesion parameter to model to have the balance, and we have developed a consumption model quite simple to reproduce qualitatively the experiments. We have good overall good results comparing to this experiment. At the plant scale, we have a stability of cavity, and it matches reasonably well the industrial observation. And the cohesion seems important only for the very fine particles that are where we have combustion. And the perspective is to test some parameters in the model, consumption, effect of consumption rate and flow rates at the plant scale. The origin of the nature of the cohesive force is not determined yet, so we have to make some experiments to better understand. And so that's the main perspective for this work. Okay, so that ends this first part, which was focused on blast furnace. The other topic I wanted to show you is for gas solid fluidized bed. So we developed some knowledge and know-how for measurements and simulating gas solid fluidized bed, where we include some solid in a fluidized bed. So that's what we include in the solid fluidized bed is one of our products is the rectangular bloom. So I will show you what we have done at the lab scale. So it's mainly some colleagues from my laboratory who worked on this subject, and another colleague, Michel Louche, who helped us to master a technique to measure solid volume fraction in solids, in granular solids. So here I will show you some context objective, how to measure volume fraction in fluidized bed using capacitance instruments, and then the coarse grain CFD DM simulations we have performed. So in particular, we are using olivine particles, and we are studying a bubbling fluidized bed. So if I put these particles in the Geldart diagram, which is density as a function of particle diameter, we are in the B, so it's a sand-like material, and we can make bubbles out of this materials. And you see the particle size, so it's particles around 100 to 200 micrometers. And here you have a very small fluidized bed system where we put these particles, so we are able to make bubbles. So we inject the gas from the bottom, and we can have an agitation of this bath composed of solid particles. And in fact, we are using this kind of particles because they have good properties for mixing. So this is why fluidized beds are usually interesting for industrialists, in fact. So here you have the experiments we are conducting. So we have a bed composed of olivine particles, and we can immerse a steel bloom inside, and we inject some gas at the bottom. And so the questions we had is, are we able to measure locally, close to the steel bloom, the solid volume fraction, and are we able to predict with numerical simulations the different phenomena we can measure? So first, to so fluidized bed, it's a quite dense system, in fact, and optical measurements are quite complicated to perform. And also because you are completely immersed in this opaque system, we need to develop some strategy to measure the volume fraction. So what we developed is it's capacitance instrument to measure solid volume fraction. So I will show you after the measurement we have done. Then the number of particles is quite challenging because you see it's 10 to the power 11 particles in this small bath. So this small bath, this bath is about 1 cubic meter, so which is quite small in fact. Huh? But we have all of these particles inside this system, and currently the coupling between CFD and DM that I presented later with these very fine particles, it's almost impossible to simulate everything. So we can rather simulate 10 million particles or 100 maximum million particles. This is why we tested this coarse-grained approach for DM with the coupling with the CFD. And we know that it can lead to some discrepancies. So this is why it's important to have experiments to check, you know, if the coarse grain is not too bad, you know. But I will explain later. So first, how to measure volume fraction in fluidized bed. So I will give you the geometry of the capacitance instrument we have used. So here, in fact, we have an electric field going from a sensor to a ground, which is a target. And in fact, we have the guard also that emanates the same electric field from there is the same electric field from the sensor and the guard to the mass. So what we measure is the electric field from the sensor to the guard. And in fact, you see that the volume that can measure this probe is a sort of donut that is half of a donut. And which is quite good is that this donut is constrained close to a solid surface. So here you have a top view, so it's axisymmetric. And in fact, in this electric field, we know the value in the air because it's something known. And in the presence of particles, we will modify, in fact, the dielectric constant that we measure with this instrument. And there is some law that exists that can permit to retrieve from the dielectric constant the volume fraction of the solid. So we have a calibration step with this procedure. So here we just put, you know, in a small cube the capacitance instrument, which make contact with these particles that are poured in this cube. It's a dense state, so we know we can measure very easily the volume fraction because we know the bulk volume fraction, which is the mass over the volume. And we know with pictometry the real density of the particles. So if we do the fraction, we know the volume fraction in a dense state. And with the Botcher and Boderwick relation, we are able to relate a parameter Kp with the dielectric constant, with the volume fraction in a dense state. By knowing that, then we can extrapolate the value of the volume fraction to a lower value by a capacitance instrumentation plus this value of Kp. So that's what we have done to calibrate. Then we have instrumented the bloom. So we have the capacitance instruments that are embedded inside the bloom, and you see the cable are crossing on the side so that it does not modify the flow close to the area where we measure. And we can put different probes. So we can put the probe on the top or on the bottom, or we can rotate and look on the sides. So we have done that. And what we observe, so we have what you can see here. So we have 3 graphs. When the probe is looking at the top, you see that the value is quite constant. And we have a value which is close to the dense state. So it means that we are looking at a sort of a heap, let's say, that is dense. If I'm looking then at the bottom, you see that we have a very large fluctuation of the volume fraction, and also that it is a quite low value. If I take the mean, I have 0.11 in the mean. And if we are looking on the side, we have another behavior, which is a larger volume fraction value, and about 0.35, and also larger fluctuations. In fact, what we can plot is 3 values. So here I'm plotting a sort of profile. So at the top, at the bottom, and in the middle. In fact, you see that the volume fraction, the mean volume fraction, is dimensionalized by the dense volume fraction. You see that at the top of the bloom, we have something very close to the dense state. So we think that we have a sort of heap building at the top. We have an intermediary value on the side where we have large fluctuation due to probably ascending bubbles on the sides and close to the obstacle. And at the bottom, we have a very small value of the volume fraction, but still we don't have zero. We don't have zero, sorry. So it means that we have a sort of bubble, but that contains some particles that are agitated, and large fluctuations are observed in this area. So based on these observations, which are very detailed, we can think about how to model that. How can I try to find a numerical model to represent this effect? So what we have used is a coarse-grained CFD-DM simulations, because we have too many particles. So I will not recall the CFD-DM because I already presented before, but I will rather focus on the coarse-grained of the DEM. So the issue is that we have too much particles. So for large-scale applications, we can have as a CFD-DM can be quite challenging to apply. So that was proposed by other authors was to increase the size of the particle and to scale the forces. So to do that, in fact, we reduce the number of the particles. So we have faster simulation, but I have to, with this scale L, which is L times the smaller particles, I have to change the drag laws by a factor L over the power 3, and also the contacts that are modified. Okay, so I have to include this L parameter to do that. Of course, it's an assumption. So what we have tried to understand if in very simple system if it has an effect. So here you have no coarse grain here, and we just trying to get the delta p as a function of the velocity. So it is known that in fluidized beds you increase the delta p, but at some point you start to fluidize, so you have a delta p that gets constant because you are fluidizing the system. And at this point you have it's a minimal fluidization velocity, and you have some relations that exist. So there is different relations that exist. We have used the one of Tonglim for fine particles. That predicts 25 millimeters per second, And here you see with this simulation, we have a discrepancy about 8.7% without any application of the coarse grain. Then what we did is to we enlarge the box, and we kept the length of the box over the particle size that were increased in this configuration. And we did the same experiment. So we have periodic boundary conditions on the sides. I forget to mention that. But what you can see is that if we increase to a very large value of L, so the coarse grain, it seems that UMF theoric is met with a similar order of magnitude of error, even with a very large coarse grain ratio, about 10. Here also it's an experiment of the bed expansion. So when you start to fluidize, you have an unsteady behavior where you increasingly enlarge the volume taken by the particles. So the porosity increases as a function of the velocity. And here you can observe that with the different value of L, we have similar behavior of expansion of the bed. So qualitatively, it seems that this, even if the L is large, the coarse grain is large, we keep some good comparison to simple experiments of starting the fluidization. Then, we applied these techniques to our fluidized bed with by including this steel bloom inside. So what we model is only 10 centimeter size. So the bloom is immersed in the X like this. So we did periodic boundary condition on the X-axis, only simulating 10 centimeter. Why 10 centimeter? Because in the literature, it's the larger bubble we can find in a fluidized bed. So we have chosen this parameter. And here we can go with this method from 10 million particles to 1.2 million of particles. So it's now we think we can do some simulation. Here we have the parameters that are used. So instead of simulating 120 micrometer particles, we are modeling 3.6 millimeter particles. So here you have results. So we attain a steady state with this simulation after 1 minute. And here on the right side, you see the particles are colored by the drag force. And on the right side, the particles are colored by the contact force. So what you can observe, there are several things. So you have less drag force at the top. You have built some contact forces and more contact forces at the top. And you have a sort of bubble at the bottom. But the bubble is about the cell size, so it's not very well resolved, let's say, for the fluid. So we need to take with caution this results. And this is why it's good to compare to the experiment. And here I'm showing some behavior of heap. So if I'm looking only on the heap without fluidization, the heap is about 35 degrees in the experiment. In the simulation is about 30 degrees. Now, if I'm looking at the fluidized bed simulation, I have an angle that I can measure with the contact forces. The angle is about 65 degrees. So it means that I have an overheap that is stabilized by the gas, in fact. So that's what we observe. We have an overstabilization of the heap at the top of the bloom. So it's something quite interesting to know. And also now in my simulation, it's quite good because I can do a lot of statistics and I can measure the volume fraction. So I can measure the volume fraction at the top, at the bottom, and also on the side at different locations. So I can have a profile of the volume fraction close to the bloom as a function of the height from the bottom of the bloom. So this is what I'm plotting here. So there is several quantities. The green is the value of the density in the dense case without any fluidization. The red line is inside the fluidized bed but far from the bloom to give you a sort of value to compare to what is happening close to the bloom. Then I can plot the profile, which is so going from 0.3 to 0.5 when we go from 0 to 1, so from the bottom to the top of the bloom. So this is the profile. If I'm looking at the very bottom, I find 0, in fact. This is why it is not shown here. But now I can compare with the experiment. So I put all together, the experiment and the simulation, with the same scaling, with the volume fraction in the dense state, because the volume fraction in simulation and the experiment are not the same in the dense state. So this is why I tried to adimensionate that. And what you can observe is that as in the experiment and in the simulation, we are close to the dense volume fraction. In the middle, we have a value which is quite similar of volume fraction. And the only thing is that in the experiment, we observe more fluctuations than in the experiments, we observe more fluctuations than in the simulation. In fact, it's probably due because of the grid cell, which is larger than the particle size. So the effect of the gas entails less fluctuations, let's say. It's more modeled in the turbulence part. And if I'm looking at the bottom, we got 0 value for the simulation, and in the experiments we have non-zero value, but still we have something close to 0. So we have a sort of bubble behavior at the bottom and a heap behavior at the top and a transition on the sides. So qualitatively we have a good behavior, let's say, by this comparison. So in conclusion, we have developed high fidelity capacitance instrumentation to determine solid volume fraction in granular solids in a fluidized bed. The experimental data are used to validate some modeling approach. So we use coarse grain CFD-DEM simulation for fluidized bed with an immersed bloom object. And we have results that are similar. We observe a heap at the top and a bubble at the bottom. And the perspectives are to conduct some sensitivity analysis in this experiment and simulation. Another alternative to do simulation is to use Euler with good closures. But the good closures might be difficult to find because we have in the same flow, we have solid states, fluidized states, and gas states. So we need to take care when using Euler, when you go to solid to liquid and gas. So it might be challenging to do that, but interesting. So I wanted to thank all the collaborators that did the work with us on these topics. And also I wanted to make some advertisement because we'll have some new PhD and postdocs opportunities soon for particles fluid topics. So we have mainly 3 topics for particles fluids. It's wet milling of ores. So it's like you have suspension of particles in a liquid, and you try to fragment the fine particles between balls. That's between large steel balls. Iron ore flotation. It's to wash the iron ore with bubble, particle, and liquid. And also porous particle smelting. So in the continuation of the PhD of Jean Robin, who are studying this physics. And also other topics on solidification and thermodynamics with other colleagues. So if you are interested, contact us, myself, Eduard, or my colleague Gassan, or both of us, and we can discuss if you want. So that's the end of my presentation. Thank you. And if you have any questions.
Slide 4, I think. Well, thank you for this super presentation. I wanted you to go back to slide 5 because there's this interesting process here. So I think that what you have here is called a shaft furnace.
Yes.
So in the shaft furnace, it's also like a fluidized bed, and where you actually deoxidize the iron ore, you reduce it. Using, in this diagram, you use hydrogen to extract the O from the FeO. But I think that, from what I understand, that in the steel industry, there are also processes not using hydrogen, but using methane or maybe syngas, CO.
Mm-hmm.
And are these other gas whose processes, which are not as clean as hydrogen, are they still producing a saving in the greenhouse gas emissions?
So what you can do is to crack methane to make hydrogen. So and I use hydrogen, but you need to have methane. And in fact, we have also some gases from other processes that we can reuse. So the gases rich in CO, for example, we can wash them and reuse them and try to valorate them and to use, the C inside this gas. And yes, so mixing gases and washing and reusing is also very interesting for us.
Oh, Stefan, please take the microphone.
Thank you very much. It was very interesting. So I have a question which is a bit more political, maybe, than scientific. It's related to hydrogen. So I guess many people have heard about the Dunkirk plant not going to be hydrogen. Can you comment on this? I mean, is it just greenwashing, or is ArcelorMittal really interested in developing hydrogen-based steel production?
No, we are interested of all the possibilities to decarbonate. So as a researcher, we are trying to investigate different approaches. Now, what is decided for one plant or another plant, it depends on the availability of hydrogen, the cost of the hydrogen. So there is many other economic constraints that need to be, taken into account. And one thing which was very positive, recently EDF signed a contract with ArcelorMittal to maintain a low price of electricity. So we know that in the next 15 years, we will be able to develop, all the strategy to use electricity-based processes to make that happen. And for instance, all this process is powered by electricity, and so all the sources are explored, let's say, to try to decarbonate. Hydrogen, we still think it might be a good opportunity, not only for France, but also for other countries, because it depends mainly on the availability of the resources. So it depends on the locations and the politics, let's say, also, which is out of my hands.
If I may just supplement, an interesting thing, depending on the region, you have more or less scrap metal available. For example, in Europe, you have more scrap metal than in other parts. So you can use this route, which is decarbonized. Stephanie.
I was wondering, but you told that it was one of your questions. Where does come from the cohesion, in the first part?
Yes.
And because I was wondering, first you said that you have to add cohesion, because when we impose an initial free surface with the shape of a sphere, it collapses. But yes, I was wondering Did you check that if you impose your flow, your gas flow, maybe you did not need cohesion because it
No,
will,
we need cohesion. It's the first thing we have done, but we have seen nothing. Only small recirculating part. And due to the charging, in fact, at the very beginning, it's very dense. So the first collapse play a role. Then it's better to impose the first cavity because it will aerate a little bit the media close to the injector. So so this is why we have done this way. But first we did what you mentioned, like just to inject the gas, but nothing was happening. So it was a surprise, let's say. So this is why we investigated all of this parameter. But yeah, at long term, if you have sufficient aeration at the beginning, you have this both counter-rotative particles, vortices that build in front of the injector, and it remains, in fact, for without combustion, it remains.
Thank you for your nice talk. I have a very naive question. I think that I did not get why it's a problem to have this. Why are you studying, this recirculation and the fact that there is a pressure drop? And
Yeah, okay.
so at the beginning, so what is the industrial problem of that?
It's a
Yes,
very
here.
good question, not naive at all. In fact, this area is very key to the blast furnace because it's where the gas can distribute to the furnace. So it's very important area to investigate because the shape can modify the distribution of the gas, and the overall pressure inside the reactor can change. So this is why this area is quite key. And in fact, if it's blocked, it's a very big problem.
So you try to increase the mixing at the end. So what you want is to have because here you have a clear separation between the size of the grain, and what you want is to increase the mixing, or there is something else that you want to?
No, it's just to have a cavity which is stable in time and where we can control. And something what we can control, what we did with that. Now we can think about new ways to control. Maybe we have seen that there is a cohesion. Can we play with the cohesion? Can we change the parameter of this cavity by playing with the cohesion or industrially? So that's some outcomes we can think about with this kind of study. And also we have other simulation tool to optimize the combustion. So what I didn't mention is that sometimes we inject some fine powders of coal in order to increase the combustion inside the raceway. And in fact, the geometry of the raceway is quite important to know to optimize how we inject these fine particles. So yes, there is other good reasons to study that.
Thank you for talking, and I have one question about the second part. And based on the configuration you used, can we define the Reynolds number and how the volume fraction fluctuation or the heap angle can relate to this Reynolds number?
Yeah, it's a good question. I don't have the answer, so I will have to check. But the Reynolds is quite high in the systems. But maybe we have to think about how to relate that.
Because I think on one page you have to calculate some rho UL divided by some. Oh yes, that's.
Oh, but that yeah. it was a simple. This is simple system where we do the fluidization. So it's not the same as when we add the bloom, but in fact, yes, you're right. Here we have some information on the velocity available, but we are always larger. In fact, in the case we consider, because we are fluidized already, so we have to calculate it. But it's quite turbulent. This is why we are using a capsule model to resolve the turbulence in this. But you are right, it's better if I put the Reynolds number. Yeah. We can calculate it, in fact.
Thank you for your talk. Maybe I missed the part. I have a small question about the temp, because I see the CFDDM calculation, and I'm wondering if the problem is related to some heat transfer. Did you consider of that?
Yes. Can we stop the recording?